Okay, so 17, the p-value. All right, so question, is your pulse rate different when you take a quiz than when you take a regular class? Test the claim that a student's pulse rate is not significantly different when taking a quiz than attending regular class. And then they give us a bunch of information about this sample. So let's copy that, figure out what's going on. So before I can do the p-value, I got to figure out what's going on, which means I got to do all the other stuff. So new page. We will get to the p-value. So let's see, we got to come up with hypotheses. So that would be this first sentence, leads us to one claim. Test the claim that a student's pulse rate is not significantly different. Okay, so, and then here they have the difference. So let's highlight some stuff. So here we have the difference. And so here, the quiz was higher than the lecture. Here, the lecture was higher than the quiz. So some students are more nervous in class than they are when taking a quiz. Others, at least they have a higher pulse rate. It's hard, I can't necessarily say they're nervous. They may be related. Not different. So different would mean it's not 0. So if two things are different, like 2 is different from 3 because 3 minus 2 is 1, right? There's a difference. So difference means not equal to 0. And then not different would mean equal to 0. So right here, they're giving me two hypotheses. One is that the mean is 0, meaning that the average difference is 0. There is no difference between the pulse rates. And then the other one would be mu is not 0, that there is a difference. And you can see here, there's always seems to be a difference. But sometimes it's high and sometimes it's positive and sometimes it's negative. So, right, so that leads to the question, is it different or not? And so because this has an equal sign in it, this has to be the null hypothesis. And because this is a not equal, it has to be the alternative hypothesis. Okay, so next thing, the average of these guys here is, called X bar, and they're telling me that's 2.7. So if I throw this into a spreadsheet, I should get 2.7. So we should try one of those pre-built spreadsheets for this. Standard deviation, I'm assuming that's the sample standard deviation because they do not say the word population there, is 9.93. And we have 10 students, so that's our sample size, n equals 10. So let's go find the right spreadsheet. So remember back last week, I gave a whole bunch of spreadsheets out. So let's go dig one up. This is a hypothesis test. And then those spreadsheets, you should either, if you're an Excel user, save them to your computer so you can get to them easily. You don't want to have to keep going back to week 9, or if you use them, if you're a Google user, they just should be in your Google Drive if you've already used them. So if I go to my drive, I should see in my recent files, I made a copy. And it was called hypothesis tests. And I can see I have a couple of different ones here. Blow this up a little. I have Gary's hypothesis test, that's a Google sheet, and then I have one called .xlsx, which means that's an Excel sheet. If you haven't yet used these or made a copy, then you would have to go back to the home page and get it to make a copy. So let's show that quick. And you don't want to have to keep going here. You want them in your drive or you want them on your computer if you're an Excel user. So this is in week 9, and there is the model confidence intervals with spreadsheets, and there was the model hypothesis test with spreadsheets. So we're doing a hypothesis test. So this is the spreadsheet that I made a copy of. And let me actually open that in an incognito window. If you're a Google user and you're logged in, you would just select Open with Google Sheets. If you're not a Google user, then there's a button over on the right that says Download. So over here, there's a download button, and then you can use it in Excel. So either you're going to open it with Google Sheets, or you're going to download it to Excel to reuse it. And oops, I didn't mean to click that. I already have a copy, thank you. All right, so once you get that, let's get mine open. Gary's, this one is here's the one I want. Now oops, I clicked the wrong one apparently. Sorry, I'm having button pushing problems. Too many programs going at once. I thought I clicked, I want where'd you go? Gary's hypothesis test. I want the Google version. There we go. So once you open the right spreadsheet, then you have to decide which tab you want. And this one I've been playing with, so I have an extra fourth tab there. But either you get to decide if you're doing a z-test, a proportion test, or a t-test. If you're doing a z-test or a t-test, you have to decide, was I just given the summary information, meaning the mean, sample size, and sample standard deviation, or was I given the actual data where I can just plug in the data and then it will calculate everything for me? So, and then you have to decide if it's a Z or a T. So let's look back at this problem. And yes, so you can use these for the final. Where's my problem? Over here. Okay, so next thing I know that select the right hypotheses. So it's the mu equals, mu doesn't equal, which means I have to do a two-tailed test. P-value on a two-tailed test is always a little harder. And this says we could run the randomization test. I'm just going to run it in the spreadsheet. They'll give me pretty similar results. So just for fun, let's go to the randomization tests. And so this is the way we did it a couple of weeks ago before we learned the formulas. Randomization test for a mean, select the correct set, and it was pulse rate difference. And it comes with the correct hypothesis here for the null. If you were editing your own data in, you would have to set the null hypothesis. And it's got the sample over here, which you can see is that mean of 2.7 the problem mentioned, and the standard deviation of 9.934. Once I have the data in and I have the correct hypothesis test, that's when we went on to generate thousands of samples. So now I have 8,000 samples, maybe 7,000 samples, each of size 10, based on this original one. And this is a two-tailed test because of the not equal to. And then I need to go set my level. So what did they say? Actually, no, I need to enter my data. Is the last step, because they only asked me for the p-value. So the p-value is based on that sample mean of 2.7. So 2.7 is to the right of 0, so I edit this number at the bottom. And so the p-value is the combination of the tails, because this is a two-tail test. I wasn't going for greater than, I wasn't going for less than, I was going for either way. The data happened to fall for the right, but I still have to look at the left too, because it's a two-tail test. So I have to add up the 1.88 plus 1.88. Randomization tests like in this and StatKey tend to be normally distributed. A T-distribution is a little wider. For this problem right here, where'd you go? Since I have such a small sample size, I should use a T-distribution, not a normal distribution. So, so my spreadsheet's going to give slightly different answer. It's going to give me a slightly, let's see, it should give me a slightly bigger p-value. No. Yeah, I think it's going to be slightly bigger. So let's calculate that. So back to the spreadsheet. And let's actually bring the data in. So either you could use the left side of the sheet and type in the 2.7 and the 9.93, or you could highlight the data and copy that in. So if the problem you're given doesn't give you the data and it just says, hey, the sample mean was this and the sample size was this and the sample standard deviation was that, you just plug them in, okay? So, but let's go through it in order. So this part right here says without sample data. Okay, so my mean is 0. And then this is just for looks, but I'm going to change that from a greater than to a not equal. And there is a symbol we can grab from the insert menu, but this is quicker, that's okay. And then our significance level, what were we given? And each time you draw, it'll be different. So I got 0.5% for my significance level. Yours might not be the same, but the data is the same on this particular problem. And then they gave the sample mean that they just told me, hey, it should be 2.7, which is what StatKey confirmed a minute ago. The sample size that I forgot is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And it's kind of dangerous counting yourself, especially on a test, and they gave me a standard deviation of 9.93. So once I type in the null hypothesis and then the sample statistics, then the computer calculates everything else. The standard error, which I'll draw out in a minute, the test statistic, which is a z-score if I need it. Oh, I wanted to be in the t-test, oh well. And then the p-value, and it'll tell me the left tail, right tail, and two tail. Now, StatKey had said it was 0.188, is that right, on my version? Yeah, so 18.8%. I have to add those two together. So let's compare that to what's in the spreadsheet. It should be similar because the z-score is normal. So if I go, what is 0.188 times 2, I get 0.376. This says it's 0.389. So this is theoretical. This is experimental p-value right here. And the problem should accept either. T-test is what I really should use, not a z-test, because I don't know the population standard deviation and the sample size is under 30. So I really should be at this tab here. And because they gave me the data, I should actually be over here on the right. So I edited this one to be a little bit more obvious, so yours might look a bit different. So I have to copy and paste my data in here. And so I need to delete whatever's there. Make sure I got it, yeah. And then I got some extra shit there, but that's not a problem. Paste in my data, hopefully it's still copied, yep. And then it says, here's your sample mean, 2.7, here's your sample size. So it looks at that column and automatically grabs these three numbers right there. We still need to set the mean for the null hypothesis. And I'm just gonna edit that one to remind myself this is a not equal two tail. Not equal, which means two tails. So even though my data fell to the right, I got to explore its symmetric partner on the left. So then down here, I get a little bit more information. T-statistics is a little fussier. One of these will usually give an error based on which side the data fell on, and that's okay. So, oh yeah, my significance level was 0.5%. Yours will likely be different. And the standard error is about the same as it said before. It's about 3-ish. And my p-value in this case for a two-tail is 412. So it's a little bigger than what StatKey calculated. And remember, StatKey calculated that 2 times 0.188 for my version, right? Your version might be slightly different. So those 37, 38%, 41%, they're in the ballpark. And this problem should take either one. But the key is, because it's a two-tail test, because the alternative is a not equal to, then you have to make sure you grab both sides. And then how to do a drawing for this. So to do a drawing for this, you need to know the null hypothesis, you need to know the sample mean, and you need to know the standard error. Not the sample standard deviation, but that divided by the square root of 10, which is what I calculate here. Let's see, I got a question. Some of the questions don't like the values I gave them from StatKey, but when I did it in a spreadsheet, it liked the data. Yeah, if the problem doesn't specifically say use StatKey, then it's going to be a little more restrictive on the answers. When I anticipated or wanted people to use StatKey, I kind of made a wider margin of error for answers that are acceptable, just because of the randomization that happens there. So if it's not clear if you should use StatKey, then you should use the spreadsheet method to make the calculations. or the theoretical normal or theoretical t from stat key, but not the bootstrap stuff. But if you do both, they should be in the ballpark of each other, right? So here I have about 40% and about 40% for the p-value, which is a huge p-value. What does that p-value tell us? So let's draw a picture and make a conclusion here. Yeah, no, it's not necessarily how stat key rounded. It's just that stat key is just because of the randomization that's involved. The answers will be a little bit different than the theory, the theoretical version. Like again, rolling a dice, we expect 1 out of 6 times to get a 5, but it's not going to happen exactly 1 out of 6 times in reality, and that's what's going on there. Okay, so back to the picture. Let's see, what was it was about 3. So I'm just going to draw a sketch of what happened in this situation, and to do that, the null, because this is a hypothesis test, the null hypothesis has to go in the middle. So right in the middle is mu equals 0, because that was given here. And then to measure what it means to be 1, 2, and 3 standard deviations on either side, that's where the standard error comes in. And according to the spreadsheet, my standard error was about 3. And to get that, you take the sample standard deviation and divide by the square root of the sample size. So for us, that was about that 9.93 divided by the square root of 10. Comes out to a little bit bigger than 3. I'm just going to call it 3 because it's easy to graph 3. So 1 standard deviation to the right would be an average difference of 3. 2 standard deviations would be an average difference of 6, and an average difference of 9. Going the other way from 0, we subtract the 3. So -3, -6, -9. And the reason I want at least a couple of those numbers is to know where the sample mean shows up. So the sample mean determines the p-value. So once I go over here and graph the sample mean, 2.7, so that would be around here-ish, probably a little closer to 3. Let me undo that. Interesting. Use the undo button. There we go. So maybe right there-ish. So that right there is me saying, hey, my sample was about 2.7. So that leads to a right tail over here. And my spreadsheet says for a t-distribution, which is technically what we ought to use here, that right tail is about 20.6%. StatQ was saying it was about 18.8. That's okay that they're a little different. So this side ends up with about 20.6%. But because this is a two-tail test, I got to remember to reflect that over this side. So the same distance away from the middle on this side, there's a mark I have to make. And I don't really care what that X value is. All I care is that I know that that tail is also 20.6% because this is a symmetric distribution. So my p-value is the sum of those. So the p-value in this case, or just double one of them, is going to be 2 times that 20.6%, which would be about 41.2%, or as a decimal, 0.041. Oops, no, too many zeros. 0.412. So that's my p-value. And again, two-tail, you got to remember, you got to reflect it to the other side and add them both up. And that's the step many of us miss. I miss it once in a while too. Okay, so yeah, that was a tough one. So my p-value to 4 decimal places, 0.41, oops, 41 something. I can't type today either. 4124 for me. And again, yours might be a little, let's see. Now yours should be the same. I can only remember what I'm supposed to type. 4124, thank you, Gary. And I forgot my decimal point, always double check stuff before you hit submit. And then that is a huge p-value, which means this is close enough to 0 that it looks like on average, people's pulse rate, students' pulse rates don't seem to be much different on a quiz or a test. is the conclusion based on this data. Okay, so, and let's submit that. And then this one, it should take that number, and it should have taken the stat key one also. So it was stat key 376. And anytime I say, hey, you can use stat key, then I make it a little more tolerance for what's an acceptable p-value given the randomization expected in stat key. Okay, question 6, question 17. Oh, I should write a conclusion. So some of the problems you get just say, hey, what's your decision? And they don't ask about the conclusion. The conclusion is what you would tell your boss or me or your mom, or maybe you're writing a press release. It's what would go in the press release. You wouldn't in a press release say, hey, we failed to reject the null hypothesis, right? That means nothing to anybody. So we have to put that in context. And there's tons of ways to word those. And it depends on what your parameter means. So my population here, I'm assuming, is all college students. My parameter is the average difference in their pulse rate from quiz to test. So, and I can't write a conclusion unless I know the parameter. So parameter, and just remember, parameter is just some measurable thing in your population. So what can we measure about students? Well, we can measure grades and heights. We can measure their age and how much they sleep. We can measure whether their pulse rate's different on a quiz or a test. So anything about a population that's measurable is a parameter. And this parameter is the average difference in pulse rate. So my point here is, if I ask you on a question to write me a conclusion, I highly recommend you write in words what you think the parameter we're measuring and estimating is first, and then you can write your conclusion. So I need to know that. I need to know my null and the alternatives to make the conclusion. The average difference in pulse rates, and then I could make a slight note here that it's quiz minus lecture, meaning the quiz rate minus the lecture rate. And it's the average difference of students. Okay, so what happened? We got a huge p-value, so we're failing to reject that the difference is 0, which means our data supports it's 0. So there's a few different ways we could state that depending on your preference. And this is kind of what we call spin, because there's many ways to word something, not necessarily a best one. So let's see. I could say there's just not sufficient evidence to accept the alternative, but I would want to say what the alternative means, because my mom was like, what do you mean by alternative? Let's start with that one. So there is not sufficient evidence to, let's see, do I want to reject the null or just say we can't accept the alternative? There's not sufficient evidence to accept. I think I'm going to go with accepting the alternative, to accept the claim that the average difference in pulse rates extra letters. And I should add in that note, it's always quiz minus lecture students. And definitely have to have the word average in there. It's not just the difference in pulse rate of a student, it's the average of a bunch of students, of all students. Students is different from 0. Average difference is not 0. Okay, so again, what am I doing? I'm saying there isn't sufficient evidence to accept the alternative, so I got to state what the alternative was. So let's just double check I got that right. The alternative, which we can't accept because our data is closer to 0 than it is farther away from 0, is that the difference is not 0, okay? So if I wanted to state that in another way, I could say that the pulse rate and the quiz rate are different. I can't accept that they're different. That's what I'm trying to say. Sure, Gideon, I can try that. So then back here, yeah, so either you could put in the not 0, or you could say that the two pulse rates are, there's not enough evidence to accept that they're different. Would be the other way to state it. And if it's one of the cases where I give you like multiple choice on which is the correct conclusion, you should always write your own first before trying to pick one of theirs. And often it's stated with the null and the alternative written in regular English. Sometimes just one of them is stated. So here, notice I'm only referencing the alternative. I could state then the data supports that there is no difference in pulse rate. So I could amend this by saying the data suggests that there is no difference in pulse rate on average. Individuals will have definite differences, right? On average, there seems to be no difference because some people appear to be more excited in a lecture than during a quiz. Okay, so that would be my conclusion. So next, I have a request to kind of give a summary of 28, 29, and 30. Let's take a look at what they are. 28, 29, and 30. Hypothesis tests with the central limit theorem, sure. So this one is about a proportion. The next one is about a mean where we're told to use the t-test. Sometimes we have to guess. Like remember as a previous example, I was guessing I should be doing a t, not a z. And then this one here, statistics students believe that the mean score, yeah. Okay, so kind of a summary of those three problems, and then we'll do one of them. Oops, page, please. So once I decide I'm doing a hypothesis test, so this relates to the flow chart I've made before. And actually I want to stop